So what I would like to do now is talk about how to use eigenvalues and eigenvectors to solve systems of differential equations. And today we're going to focus on the case that the matrices that we construct have eigenvalues that are real numbers, not complex numbers. And what we'll talk about the next 2 days is how to deal with the complex valued case. Now, we will be focusing in this section on systems of differential equations with a rather specific format. What I want is a system of equations where x prime and y prime are given as a sum of number times x and number times y. A differential equation, a system of differential equations in this format, is called homogeneous because there are no functions of the input variable. It's all output variables here. And it's said to have constant coefficients because there are just numbers on all the x's and all the y's. So very similar to homogeneous single differential equations with constant coefficients, the only thing that's different now is that we're dealing with a system. We're dealing with two of them that are sort of intertwined, interconnected. Now, corresponding to every homogeneous system of differential equations is a matrix, a 2 by 2 matrix. And that matrix can be constructed by reading off the numbers, the coefficients on x and y in your system. The matrix that I will associate with this particular system of differential equations just has the constants A and B and C and D as the four matrix entries. As a quick example, if I had the system x prime is equal to 2x plus 3y equals 4x minus 5y, then the associated matrix would be the matrix that has 2 and 3 and 4 and minus 5 as its entries, the coefficients of x and y in this system. Now, when you're building the matrix, you've got to be very careful to make sure that both the equations in the system and the terms in the equation are in this exact order, x first, followed by y. So for example, if somebody gave me the system y prime equals 2y plus 3x, x prime is equal to 5x minus 2y. If I tried to construct the matrix by reading off the coefficients in this order, then this matrix would not be useful to me as a tool in this problem. Instead, in order to make the matrix useful, I need to reorder these terms and these equations so that x comes first, and so now that x is first both in the list of equations and in the list of variables, the matrix that I would be able to make use of is 5, negative 2, 3, positive 2. That would be the useful one. Now let's talk about how the eigenvalues and eigenvectors of this particular matrix are related to the solutions to this system of differential equations. So theorem, we have a system of differential equations homogeneous with constant coefficients, and we have built the associated matrix A, B, C, D. We go into the matrix A, and we start by finding its eigenvalues. Let's call those eigenvalues lambda 1 and lambda 2. Let's call the corresponding eigenvectors k1 and k2. With these eigenvalues and these eigenvectors, the solutions x of t and y of t to this differential equation satisfy the following vector equation. Must be equal to eigenvector number 1 times c1 e to the first eigenvalue plus eigenvector number 2 times c2 e to the second eigenvalue. Let me show you what it looks like to use this theorem in practice. Someone says solve this system of differential equations x prime equals negative x plus y, y prime equals 4x minus y. Now I could solve this using method of substitution, and in this particular case, I suppose it wouldn't be so bad. But as an alternative method, I could pass to the matrix negative 1 on x, positive 1 on y, positive 4 on x, and negative 1 on y, and I could study the eigenvalues and eigenvectors of this matrix and use them to assemble the solution. Now, the eigenvalues of this matrix are ones that we have already found, both in yesterday's video and in the one before that. We have already found that there is an eigenvalue of negative 3 and an eigenvalue of positive 1. And we have also found that these two eigenvalues correspond respectively to the two eigenvectors. Was 1 comma minus 2, and the other one was 1 comma 2. So using these values, let's go ahead and assemble the solution. The solutions, according to the theorem, must satisfy the following vector equation. X of t and y of t must be equal to the first eigenvector times c1 times exponential to the first eigenvalue times t plus the second eigenvector times c2 times exponential to the second eigenvalue times t. Now, by looking separately at the top entries and the bottom entries, you can deduce the values of x of t and y of t. X of t must be equal to 1 times c1 e to the negative 3t plus 1 times c2 e to the positive 1t. And then by looking at the bottom entries, you can deduce what y of t must be doing. Y of t must be equal to negative 2c1 and positive 2c2. And these are the two solutions to the system. So quite an elegant way of finding both solutions simultaneously. One of the nice things about it is that it doesn't actually require any derivatives or calculus at all, right? All you have to do is set up the matrix, find the eigenvalues and find the eigenvectors, and assemble them appropriately, and you will find the two solutions to the system. It's quite elegant. To demonstrate this process from beginning to end, let's solve the following system of differential equations. Now, this is a situation where I think that I personally would be really interested in solving via an alternative method, solving by some method other than method of substitution. Because if I solve this equation using method of substitution, I can already anticipate that pretty much no matter how I try and isolate a variable in either one of these equations, I'm going to end up with some relatively nasty fractions. So instead, let's pass to the matrix that contains the coefficients on x and y in these two equations. And let's use the eigenvalues and eigenvectors of this matrix in order to solve the system. So I'm going to start by finding the e-values, the eigenvalues. So I'm going to subtract lambda from the entries on the diagonal. And I'm going to take the determinant of that matrix. And that'll give me 32 minus lambda, negative 34 minus lambda, minus negative 12 times 90. So after some simplification, that looks like negative 8, if my calculations are correct. 12 times 90 is 1080. And then 32 times 34 is 1088. So the difference is 8 units. And if I set that equal to 0, then I find that the eigenvalues are given by negative 4 and positive 2. So now let's see what the eigenvectors are corresponding to these two eigenvalues, starting with lambda equals negative 4. If I set lambda equals negative 4, and I subtract negative 4 from each entry on the diagonal of the matrix, then I get 32 plus 4, which is equal to 36. I get negative 90. I get 12, and I get negative 34 plus 4, which is negative 30. I seek a vector, v1, v2, for example, which becomes 0 after this matrix is applied. And as has been the case consistently, the second row in this matrix is just 1/3 of the top row. So there's some redundancy in here. I don't need to consider both the top row and the bottom row. I only need to get the first row times the vector to equal 0. So, taking the cheapest path, which requires the least amount of brain power, I could, for example, set v1 to be equal to 1, and then v2 would be equal to 36 over 90 to compensate. So my first eigenvector, corresponding to my first eigenvalue of minus 4, is the vector that has 1 in its first entry and 36 over 90 in its second entry. Then, looking at eigenvalue number 2, which was in this case literally the number positive 2, if I go into my matrix and subtract 2 from the diagonal entries, then I get 32 minus 2. I get negative 90. I get 12. And I get 34 minus 2. Negative 34 minus 2. Which becomes 30, negative 90, 12, and negative 36. And it's a little bit harder to see here, but once again, you can confirm that equation number 2 is actually a scalar multiple of row number 1. So I'll focus my effort on row number 1. And I will try and get V1s and V2s that get that product to equal 0. And once again, taking the cheap route, I'll set V1 to equal 1 and force V2 to compensate. And it looks like V2 would have to be equal to 1/3. So my second eigenvector would be 1 and 1/3. That would correspond to the eigenvalue of 2. Almost done now. The only thing that we have to do is assemble the solutions x and y. X is equal to 1 times C1 times e raised to the first eigenvalue plus 1 times C2 e raised to the second eigenvalue. And y of t is equal to the 36/90 times that expression plus the 1/3 times that expression, looking at the bottom parts of the eigenvector. You can write it in this form if you want to, or if you prefer, you can write this in a more traditional format, looking at these top entries to get info about x, and then looking at these bottom entries to get info about y. That is how I use eigenvalues and eigenvectors to solve systems of equations, in particular in the case where the matrix eigenvalues are real.